Hi everybody, this is Mr. Folly, and welcome to podcast 1.2 for Accel. This lists all of the stuff, and I'm afraid my podcast will be long, so I'm going to skip that and let you write that down if that makes you happy and hot. The strong force holds the nucleus together. So the energy comes from E equals mc squared. This converts a bit of mass into a lot of energy and risks the repulsion of protons or protons. Remember, protons are positive, and positive repel. So what keeps my nucleus together if it's a bunch of positive stuff? Wouldn't they all repel each other? Of course they would, but there's the strong nuclear force. So all you need to know is strong nuclear force holds the nucleus together. Atoms often decay into more stable atoms. Now this is mildly surprising for some of us. We think atoms are eternal. They're not. Atoms that do not fit on this band, we've noticed that only these atoms are stable. All other atoms do radioactive decay and turn into something more stable. So if I am element with atomic number 50 with 20 neutrons, so atomic number, remember this is protons, so if I have 50 protons and 20 neutrons, I'm unstable, and I will decay and keep decaying until I become a stable atom. So guess what? These guys are more abundant in the world, and these guys are rarer. E equals mc squared also explains why nuclear power releases so much energy. So I forgot to actually talk about that. E is energy. M equals mass. And in nuclear reactions, a bit is destroyed. So an itty bitty little bit is converted. I shouldn't say destroyed. Is converted, but I wrote constructed. Converted to energy. So like E equals mc squared, so some of the mass is going to get converted into energy. And then c is the speed of light, which we know is a huge number. The speed of light is, I think, a 3.00E8 meters per second. So if I square that, it becomes huge. I'm going to cough. Excuse me. So that means it's a huge amount of money because you're multiplying it times a huge number squared. So that's why nuclear power creates so much more energy, bigger bombs, bigger superheroes. Even Yoda is buff. In the beginning, there were protons. If you remember, protons are hydrogens, right? Hydrogen has one, and typically hydrogen is 1 and 1. So what happened in the beginning is there were these very simple little parts, like little bitty Legos, and as the universe went on, they all would come into each other and smash into each other, and there would be this big bang. Well, first it'd be these big massive particles, and then there was so much energy in here, it shot out. So when there was all this energy, the hydrogen smashed into another hydrogen, so 1 and 1 makes 2, which would make, and then helium could either smash into this or smash into another helium. But there's a lot of smashing going on. So here's a little demo of this. So if I have carbon-12 and a helium, it could smash and make oxygen. Oh, okay. And if I have silicon smashing with another silicon, it can make iron. Woo, big, right? So those reactions can take place in the stars. And then, like I said, when those things are very high energy and they blow up, that means that all these elements are there and they slowly collect and they make planets, and then they make people. So we are all stardust. Oh, maybe not Danny though. I did that one already. Half-life. Atoms decay by half-life. Most things are a linear trend. I work every day 3 hours at a car wash, and my money gets bigger and bigger and bigger and bigger, and it's linear. Half-life doesn't change like that. It changes like this. Half-life is the time it takes for half of a substance to turn into something more stable. If the half-life of iodine 129 is 30 minutes, how much of it is left in 120 minutes if I start with 250 grams? Now this is kind of a table-ish kind of thing. So I start with 250, and I know every 30 minutes I lose half of it. After 30 minutes, I'm going to have 125 grams. Another 30 minutes, so 30 and 30 is 60, right? So my total is 60. I'm going to have 62.5 grams. Another 30 minutes will put me at 90. and that would give me 31.25 grams. And then another 30 minutes would get me to 120, and that would give me to 15.6 grams or so. Okay, so that's how much is left. So you just make a little table, count it down, and make sure you can keep track of how much time is left. Okay, it's a little neater if you do like mass, time is 0, 250, 30, and you get the idea. Another half-life sample question. An isotope of sulfur went from 100 grams to 12.5 grams in 33 minutes. What is the half-life? So what I'm going to do is I'm going to figure out how many half-lives. How many? So if I go from 100, and then I'm going to keep cutting it in half until I get 12 and a half. 100 to 50 to 25. Half of 25 is 12.5. So that took 1, 2, 3 half-lives. So 3 half-lives. So 33 minutes equal 3 half-lives. So half-life equals 33 divided by 3, 11 minutes. Ah, and we'll do a whole bunch of those, but one sample should be enough. Half-life helps us date things. All living things and things that come from living things have carbon-14 in them. And it's rejuvenated to a constant rate. Have carbon-14 in them at a constant ratio. Now, carbon-14 is not the most stable form of carbon, but for some reason, living things make our carbon-14. It has a constant half-life of around 5,900 years. We can tell how old mummies, cavemen, tools, and the clothes of ancient cultures are because those things are made of carbon. Oops, I tried to put E. Carbon, that's just a scribbling. And they're old. If the half-life is like 5,900 years, it's got to be really old to have a significant amount disappear. We can't tell the age of murder victims because they are too recent. So if I found a dead body in my backyard, I can't use carbon dating to find out what time they did because it's too uncertain. Okay. Nuclear reactions. 2 conditions must be met to balance the nuclear equation. Conserve the mass number, that's the top number. Conserve the nuclear charge, the atomic number, that's the bottom number. So top and bottom have to equal each other. Well, okay. Get out your calculators. 232 is on the left. This is a yield sign. So thorium turns into radium, and this is an alpha particle. 232 has to equal 228 plus 4. Hey, that equals 232. 90 equals 88 plus 2. This yield sign is the same as an equals. You have to use yields in nuclear and chemical reactions instead of equals, but it's the same thing. 90. Hey, if this is 91, oh, this is negative 1. Oh, I see. Okay. And then all of these have to match. Now, if I put a coefficient in front of this, this means I have 3 n's, which would be the same thing if I didn't put a 3 here. I could have plus 1, 0, n, plus 1, 0, n. By the way, this dude right here is a neutron. Right? I'm sorry I'm going so quick. I'm trying to keep this a reasonable podcast. Alpha decay. Alpha particle is a helium nucleus. Okay, helium nucleus is helium 4 over 2, and it's positive, so it's plus 2. It's big for a particle. It's heavy, and it's positive. But because it's so big, skin can block it. Paper can block it. Okay. Decay means that it's a product. So 20984 Po undergoes alpha decay. That means I need to have an alpha particle, which is 4 over 2 He. Don't worry about the charges. The electrons don't matter here. So the top number is going to be 205. The bottom number is going to be 82. Now, I don't know what this dude is. So I have to look and see what atomic number 82 is. And it is everybody's favorite, plumbum. That's lead. Beta decay. Kind of same thing. This is what a beta particle looks like. 0, -1e. Sometimes it's shown as 0, -1 beta. It's a radioactive nucleus that undergoes beta emission, has a neutron, remember neutrons are neutral, mass of 1, converted into a proton, hey, that's 1 over 1, and an electron, and it ejects the electron. An electron, hey, that has no mass, and that has no protons. Okay, but notice how this 0 turns into a 1. So this guy right here, the beta particle, is really a -1. Okay, and it's negative because it's an electron. For example, tritium, which you don't need to know that, tritium is 3,1, a radioactive isotope of hydrogen, undergoes beta decay. Again, it's decay, so my beta particle is going to be a product. 3 equals 0 plus 3. 1 equals -1 plus 2. Looking at the periodic table, number 2 is helium. Beta decay is higher energy, but can be blocked by a sheet of plastic or metal, which is tougher than paper or skin. Gamma emission. The nucleus is too high of energy and releases energy. The energy is massless, and so is gamma. Gamma is shown as 0, 0. Not much of a change for our purposes. It is chargeless and high in energy. Takes feet of lead to block it. Cerium-141 undergoes gamma. Cerium is Ce-141, and if it undergoes gamma, 0, 0, whee, plus 141 cerium. I don't have a periodic table, so you can look up what those bottom numbers are. Band of stability. There's a little more. Atoms are stable with the right ratio of protons and neutrons. We saw this before. Hey, you should draw this. Or something like it. Just know that it curves up. Atoms do different types of decay to get back on the band of stability. Now notice this stops at 83. Okay? Anything that is above 83, actually it's 83 and above, does, notice these are big atoms, alpha decay. That's alpha. Okay? Anything that's over here does beta decay. The reason why it does beta decay is because it makes protons. So if I'm over here, to become more stable, it moves me over here until I have enough protons. And this over here, we don't really need to worry about. Okay? So if you draw this and you know that beta is what you do if you're here, and alpha is what you do if you're bigger than 83, and this one is other, then you're all set. I'm going to skip past the next thing, which is just a longer way of writing what I just drew. If you like to look at it, you can. Nuclear fission. This is a great picture of nuclear fission. You can draw it. You should. Fission is where the splitting of a heavy nucleus into 2 or more lighter nuclei and some neutrons. I shot a neutron. It's unstable. It shoots into smaller things and some neutrons. Big guy. Hit it with a neutron. Smaller. Smaller. Big guy. Hit it with a neutron. Smaller. Smaller. See, 235 is the big number. These are both smaller. 92 is a big number. These are both smaller. As long as one of them is smaller, it's okay. Okay. So fission splits it. Fusion is where 2 things combine. Okay. So what could happen is 4 hydrogens can mash, and you get 4. Now you wouldn't have to predict this exactly, but it gets bigger. Notice this is bigger. You get at least one thing that's bigger. Okay? Small, small, bigger. Small, small, bigger. As long as you're making something bigger, you're doing fusion. Fusion requires energy. Lots of energy. Because you smash 2 repelling positive nuclei together. So why isn't fission so hard to start? Are neutrons repulsive? No, neutrons aren't repulsive. Now, neutrons aren't all that attractive. It's not like, oh yeah, neutrons come here. They're not attractive. They're not repulsive. It's fine. We are gone. Well, maybe this wasn't too long. So I will say this to you. Toodles.